So students, after having explained capacitance in my two previous videos, what is a capacitor and how the capacitance is derived for the parallel plate capacitor. So we'll go further ahead and we'll discuss about the capacitance, dielectrics, capacitance which are connected in series and parallel in this video. So for the revision, I am just writing again. Capacitance is defined at C is equal to Q upon V, or in a parallel plate capacitor, C is given by epsilon naught A by D, where A is area of the plate and D is the separation between the plates. And you must remember that V is equal to E into D, where E is the electric field which is in between the parallel plate capacitors, the value of which is given by sigma upon epsilon naught. You can refer to my previous videos for all this. Now, this is just for the revision purpose that I have written down V is equal to E into D. This is very important and you must understand this. That's why it is being put as a revision part always in each of my videos. Now, in this case, if Q is C is equal to Q upon V, and if fundamentally if we reduce E, because E is dependent on V, by this formula E is dependent on V. If we further reduce E in between the conductors, then we can store more energy per unit volume. So that is the concept where the dielectric comes into the picture. Because by introducing the dielectric, as we will see further, we increase the capacitance of a capacitor. The concept of total increase in the capacitance is achieved by reducing the electric field between the two plates of the capacitor. So dielectric is basically an insulator. The electrons remains attached to the individual atom. You know that in an insulator, they remains attached to the individual atom or molecules. However, the moment they come under the influence of an electric field, so the effect is there is a microscopic movement. So this microscopic movement give rise to the polarization of the atoms or the molecules. So dielectric is substance which does not allow the flow of charge but permits them to exert electrostatic forces on one another through it. So dielectric is essentially an insulator which can be polarized through small localized displacements of its charges when it is brought under the influence of an external electric field. To explain it, let us understand difference between the conductors and dielectric. So it is under the influence of an electric field E naught. So what is happening? The polarization of a conductor happens because there are free electrons. The total free electrons goes to one side and negative charges come onto the other side. So what happens? The induced electric field develops in the conductor. So it nullifies. So this happens till external electric field becomes the induced electric field inside the conductor. So the net electric field inside the conductor is 0. Whereas in the case of a dielectric, there is a polarization which is happening. Polarization will allow positive charge to develop on one phase and the negative charges come onto the other phase, but the electric field, the induced electric field in this case is not equal to the external electric field because they are insulators, so they allow only the restricted movement. So the polarization of the molecules or the atom happens and there is an induced electric field which is opposite to the external electric field but is not doesn't become equal to the external electric field like in the case of the conductors. So the net electric field inside the dielectric gets reduced. Hence, by introducing a dielectric, electric field between the parallel plates is reduced and thus V is reduced, resulting in higher capacitance with the same shape and size. So the ratio of original electric field and the reduced electric field in the dielectric is constant and is called a dielectric constant. So which is denoted by a small letter k, kappa. K is E naught by E, which is I can write as E naught divided by E naught minus EP. Here EP is the electric field which develops due to the polarization of the molecule. So you must understand what is the dielectric constant. Now with this we come back again to the concept of capacitance and we'll check how the capacitance is increased when the dielectric is introduced between the conductors of a capacitor. I have just explained that by introducing a dielectric in between the two parallel plate capacitors, electric field is reduced, thereby reducing the voltage and allowing more charge to store on it. So capacitance is increased, which we will explain now. As I have written above, E naught is the electric field which is in the free space, and I have introduced a dielectric slab which is dielectric slab of thickness T. So here in between this, the electric field is reduced, which is E naught minus EP. So, with dielectric, capacitance is given by epsilon naught A by D, where V is equal to E into D. And with the dielectric, it is given by E naught times of D minus T plus ET, because when a charge travels from the negative to the positive side, d minus t is the length in which the electric field is E naught, and there is a length t in which the electric field is E, so which is derived from this formula. So V is equal to E naught times of d minus t plus Et. Hope you would have understood this. This is very important part. So in our previous videos, we have clearly explained that the electric field between the two parallel plate capacitors is sigma upon epsilon naught, and in the previous article we have explained that if there is a dielectric, then net electric field inside the dielectric field will be given by E naught by K or sigma upon K epsilon naught. So we have substituted the values of E naught and E naught and E in this equation 1, and we have got V is equal to sigma upon epsilon naught D minus T plus sigma upon K epsilon naught times of T. The value of E naught and E are substituted in this. So V is equal to Q upon epsilon naught A D minus T plus Q upon K epsilon naught A times of T, as sigma is Q upon A. So by rearranging, we got the capacitance Q upon V is equal to sigma naught A divided by D minus T plus T by K. Hope you would have understood that capacitance, when there is a dielectric slab of thickness T is introduced between the parallel plate capacitor, is given by this formula, which I am enclosing in a box. Now therefore, for two such slabs, if there instead of one slab we have two slabs, then C will be given by epsilon naught A divided by D minus T1 plus T2, because there will be two slabs, plus T1 by K1 plus T2 by K2. So we can extend this formula for n number of slabs. Now we come to the case when the total space between the two parallel plate capacitor is filled with the dielectric. So the thickness T becomes the D. So we are substituting the value of T. So here T is being substituted. You can see here T is substituted here with D, and here also the T, which I am putting it here as a tick, is substituted with D. So D minus D is 0. The whole formula becomes epsilon naught A divided by D by K. So K epsilon naught A by D. So the capacitance increases by K times. So this is the advantage of introducing a dielectric between the parallel plate of a capacitor. This is in general true for the capacitors of all shapes and sizes. We now come on to the combination of capacitors in series and parallel. When capacitors are connected in series, you can see here the charges are equal on all the capacitors, but the voltage gets divided. So by using the formula, we can divide the voltage between the capacitors as V1 is equal to Q by C1, V2 is Q by C2, and V3 is Q by C3. So these values are substituted in equation 1. You can see here, this is equation 1, all values are substituted, and we get the capacitance when they are equivalent capacitance when they are connected in series as 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. You must remember that the charge remains constant when the capacitors are connected in series, but the voltage gets divided. Now students can attempt questions of capacitors connected in series from textbooks. We come to the Now we come to the case of a capacitor connected in parallel. So when they are connected in parallel, the voltage between each capacitor remains the same and the charge gets divided. So this is exactly opposite to what happens when they are connected in series. So Q is equal to Q1 plus Q2 plus Q3, and if the equivalent capacitance is C and the voltage is V, then the total charge is given by Q, then Q is Q1 plus Q2 plus Q3, you must have understood. So CV is equal to C1V plus C2V plus C3V by using the formula of capacitance, and C is equal to C1 plus C2 plus C3. These are simple steps you can easily practice and do. And the points to remember in this is that voltage remains the same across all the capacitors and the charge gets divided. So students can practice the various examples from the textbooks on these two formulas. Now we come to an important thing which might have not been understood by many of the students but is very important. When what is the force between the parallel plates of a capacitor? You can see, and as we know that if there is a positive plate, here is a positive plate which is having an electric field which is given by sigma upon 2 epsilon naught, sigma upon 2 epsilon naught, and this negative parallel plate is under the influence of this electric field. If this is under the influence of this electric field, it will experience a force which is given by minus q times of E. Minus is because it is an attractive force. So I have substituted the value of E. So the force between the two parallel plates is given by minus q upon 2 epsilon naught A. Minus sign of course signifies that the force is an attractive force, and the magnitude is given by q upon 2 q square upon 2 epsilon naught A. Now what is the energy stored in the capacitor and what is the energy density? As I have already explained, there is a force F which is acting in this direction when the two parallel plates are next to each other. So this is the force. So to overcome this, we have to apply a force in this direction. If I have to separate them by a distance, we have to separate them by a distance d, then I have to pull it away. So by pulling it, we have to move a distance d by this force. So work done will be F dot d. So Fd cos 80 degree, because the displacement, which we call as displacement and force, they both are in the same direction. So W is q square upon 2 epsilon naught A into d. You can understand I have rearranged everything here. So d 1 by 2 into d by epsilon naught A into q square. So by rearranging, I have got the formula W is 1 by 2 q square by c. So by looking at this, you can understand I need not to repeat all these steps. And another form is W is equal to 1 upon cv square when I put q is equal to c into v. So there are two formulas, which is 1 by 2 q square by c and another is 1 by 2 cv square. Now energy stored per unit volume. Energy stored per unit volume is given by, that is the energy 1 by 2 q square by c I have substituted here, and volume is A times of d. A is the area of the plate and d is the distance between them. So we know that E is equal to sigma upon epsilon naught. So we have now found out Q is equal to epsilon naught A into E. So substituting the value of Q here in the form of epsilon naught A into E, and by cancelling the terms which are in numerator and denominator, I get the energy density U as half epsilon naught E square. Though we have derived this for the parallel plate capacitor, this is in general true for all electrical regions where the electric field is E. So you must understand that the energy density will be given by half epsilon naught E square wherever there exists an electric field E. So this is all about capacitance. You can practice numerical formulas on this, and you can download my app which is available in the App Store, Academic Dojo, where you can ask various types of questions which you are not understanding to me, and I am there to explain you all those. Thank you.